and draw the plane. But more importantly, once you draw the plane, the next thing we are going to do is essentially about the atomic structure within that plane. So we want to use certain arguments about the atomic arrangement in those planes. So you need to be able to do that. All right. I think it's better if you speak up, because I'm very, very good at, my eyesight is not all that great, and I cannot be peering at the stuff that you guys are writing there. I see a thank you note there. Yeah, that's great. But we need to just speak up, unless you have some problem with that. Okay, I see another message. Just ask the question, all right? If you want me to repeat the question, I can do that, but just ask it using your voice. This chat business, you guys seem to be comfortable with it. I am not. First of all, my eyesight is not all that great, and the screen here is pretty tiny. Okay, any other questions? Okay, here's a question that I will ask you. We have done BCC, FCC, and simple cubic. Why not a base-centered cubic? What's wrong with that? Somebody will have to come up and answer.
So you had mentioned it last time. The symmetry of the cubic cell would be destroyed.
Okay. Suppose the AB phase, the phase containing the A vector and the B vector, that is the one along the x-axis and the one along the y-axis. So that plane, let us say, has a lattice point at the center. Okay, that means that is the bottom phase, right, of the cube. And if you have something similar on the top phase also, then it would qualify as a base-centered cubic. So what is wrong with it? It is already included somewhere else, but you tell me what is wrong with it. What symmetry is broken?
The threefold symmetry along the body diagonals.
Okay, anything else? But something easier.
The fourfold symmetry across four of the faces.
Three along three directions. Along three directions.
Yeah.
Okay, but it retains one of them.
Yeah.
Which one?
Along the base centers.
Okay, that's a good answer. Basically, it is an axis parallel to the C direction. Okay. Yeah, it is also through the corner atoms. It's okay, but it is a C axis or an axis that runs through the base centers. Either of them would work. So the fourfold remains there. So what would you call such a lattice?
It would be tetragonal, right?
Okay, tetragonal. Okay, but if you look at the tetragonal list, still there is no such thing as a base-centered tetragonal.
But you could connect the what do you say? Centers, like the so-called end-centered part, to the corners, so that half the base diagonal is covered.
Then what happens?
And you just get
what does it become?
Primitive tetragonal cell.
Primitive tetragonal. Yeah, that's great. So here's another question. So what if you have an FCC? In the FCC lattice, there is nothing at the body center, right? But what if you have a cubic lattice that has a lattice point on the face centers as well as at the body center? It's not, it's already included somewhere else. Where is it included? That's what I want you to find out.
Wouldn't it just be a smaller primitive cubic cell?
Yeah, but I want people to see that.
Okay.
Okay, so here's the interesting part. What did you learn as a structure of sodium chloride? You would have studied it somewhere or the other.
It's an FCC structure, right? But with something at the center of the body diagonal as well.
Okay, but is that what you were taught? In which case, I mean, you were taught very well. We all learned it as a different thing altogether. So I just want you to.
That's what I remember we were taught it as.
Okay, cool. In which case you were taught very well indeed. So one of the next topics is going to be looking at the void spaces, because all said and done, even in FCC with the best possible packing, you get only 74% of the volume that is filled up. So there are void spaces where, I mean, smaller atoms or smaller ions can sit. But of course, if the atoms or ions are bigger than that small space, then it just expands the lattice. So in ionic solids, that is definitely what the ions would want to do. Because of this positive charge and negative charge on the ions, they would want to sit next to each other. And so if there is, well, which of these two is a smaller of the two of the ions? Sodium or chloride? I mean chlorine.
Sodium's the smaller ion.
Okay, so let's say the FCC is based on chlorine ions. Okay. If there is something at the body center, then body center is just one site per unit cell.
Yeah.
But in FCC, yeah.
It would be, there'll be a sodium at the body center and there'll be a sodium at all the edge centers as well.
All the edge centers, yeah. Again, you had 12 edges and each edge is shared by 4 of them. So therefore that would account for 3 more sodium ions. Therefore you get this 1-to-1 ratio, which is what this stuff really wants. So you get that. Okay, I mean, we are all trying to paint word pictures by speaking about them, but would you be able to make this connection? I mean, would you be able to draw it and then see for yourself? That's what you really need to do to get the hang of the atomic arrangements and the locations and so on. The other thing is, how many of you have heard of zinc blend, which, by the way, is the first structure solved by the Braggs. I mean, it's called the zinc blend structure. Does that come again?
We've heard of it. We studied it.
Yeah, I don't know what it is used for. I have no idea, but it is called the zinc blend structure.
Repeat what you said now. What structure? You are not.
Zinc blend, ZnS, zinc sulfide.
If I'm not mistaken, it had something to do with like the tetrahedral voids being filled, like the alternate tetrahedral voids being filled.
Okay.
And
all right. I mean, I would like to know where you learned this.
We learned it in 12th grade.
Oh, okay. That's pretty neat. So there is.
But which blend
yeah.
are you talking about?
People
so zinc blend structures like salarite and bauxite.
Zinc blend. The structure itself is called the zinc blend structure. Yeah.
So, but it exists in 2 forms, right? One is the salarite structure and the other one is the woodsite structure.
Okay, so this is, I mean, science quiz territory. I have zero idea about it. I know about the zinc blende structure. It is called that. And it turns out that it is one of the first structures. I think the first structure solved using XRD. And I think Bragg himself had a hand in it. Yeah, anyway, go on. Since you asked me about sphalerite, I'll find out what it is and come back to you. I have no idea.
So the normal you
Go on.
got that CCP array and with the tetrahedral voids being packed. That is basically called the sphalerite one.
Okay, I mean, what is CCP again?
The FCC structure, I mean the cubic close pack.
Cubic close pack. Okay, that is the FCC structure. Okay, and in FCC structure there are 4 atoms forming the per unit cell, right? FCC lattice.
Yes.
And if you look at the tetrahedral voids, there are 8 of them. So zinc,
yes, half of them have to be occupied.
well, that is called the zinc blende structure. But you are mentioning sphalerite. I have no idea what the sphalerite is.
Okay, so it has got another polymorphic form as well. I mean, the wood.
Okay, I mean, maybe there is. I will find out and come back to you. Similarly, yet another solid which has this 1-to-1 ratio, and that is, again, it goes by the name cesium chloride structure. Cesium chloride has this structure. So you have probably seen this as well?
Yes, sir.
Yes, sir.
Okay, what is it? Somebody can explain it?
It's basically a body-centered lattice. The center is occupied by one of the atoms and the corners by another.
Okay, here's the deal. Once the center is occupied, body center is occupied by something different from that occupying the corner site, then it is no longer body-centered lattice, right?
As in the structure, it's technically a cubic lattice with a in the central void.
Yeah. So that is one of the things that I mentioned in the first slide itself. So one talks about crystal structure as something that is made up of a lattice and a motif. And in all these cases that we talked about, right? So we are essentially using this idea that each motif in, the motif in each of these cases, zinc sulfide, sodium chloride and cesium chloride, the motif has 2 pieces, well, 2 ions if you want to think about them, 2 different entities, and so they all sit on a lattice. In the case of cesium chloride, it is simple cubic lattice with 2 atoms, the 2 distinct atoms. The second atom happens to occupy the body center position, and in a similar way, the sodium chloride is FCC lattice with 2 distinct ions per lattice, and they occupy the positions that we already talked about. Basically, chlorine, ions, they occupy the FCC lattice sites, and the sodium ions occupy, which are smaller, they occupy the what would normally be called the octahedral void sites. And similarly, zinc blende also has something similar. It is FCC with, let's say, zinc occupying the FCC sites and sulfur atom or ion. I don't know what it is. I think it's a covalent solid. So sulfur sits at a position which is away at from the corner position at 1/4, 1/4, 1/4. So at that distance. So again, these are things that one needs to. In this mode, we are basically painting a word picture using all this dialogue, but you need to sit down and do these things in your notebook so that you are able to see this how they work out. In other words, if you take cesium chloride and do XRD, you will get a pattern, XRD pattern, which is distinctive for the simple cubic lattice. In other words, if you imagine that as a body-centered cubic lattice, then you would get a different pattern altogether. We will look at what those differences are. but you will get a simple pattern that is that comes from a simple cubic structure, a simple cubic lattice. Um, but for convenience sake, we think in terms of the second one sitting at the body center, which may, the moment we mention body center, I mean, people jump the gun and get to body-centered cubic lattices, but it is not. Yeah, somebody wanted to say something. So this idea of stuff with motive is something that you need to wrap your mind around. It's not that difficult, but yeah, it's a good idea to think about how it works out. Any other questions you may have so far on everything that we have done? Okay, since there are no further questions, we'll stop now, and we'll meet again tomorrow.
Thank you, sir.
All right, yeah, bye.